Nice to be here. We've got a lot to get through in a short amount of time, though I guess, unfortunately for you all, the main attraction, Kunal, could not join, so you're stuck with me for a little bit longer, but so it goes. I'm starting off this talk with a question, and it's not rhetorical, so I actually would love, given the intimate audience that we have here tonight, a show of hands. Do you do AutoML? And I'm not expecting a lot. Perfect, awesome. That was a great amount. All right, so for those who are doing it, hopefully you'll be able to take something away when I get around to pros and cons and why I think it is or is not useful. And for those of you who aren't doing it, hopefully you'll at least leave tonight knowing what AutoML is and roughly how it works. And as Alex said, my name is Nowak. I work for Dataiku. How you pronounce that, it's quite complicated, but we're a French data science platform company. What does that mean? It's like all the buzzwords in one. If you want to talk more about what data science platforms do and what we at Dataiku do in particular, you'll get a little bit of that in this talk, but not a lot. This is not meant to be a sales pitch, but more just a discussion of a concept in the space. So if you want to talk vendors, which probably no one does, but if you want to talk, I'm here. Let's chat afterwards. So a couple things. First of all, who am I? My name is Nowak. I'm a solutions architect. Sorry, I need to move around so I can see around the pillars. My name is Nowak. I'm a solutions architect at Dataiku. What does that mean? It means that I work with our clients, mostly Fortune 500, Fortune 1000 companies, helping them think about kind of their data stack, their AI stack, their analytics stack, again, whatever term you want to use, and how we may or may not fit in as a solution that could enable their developers. Previously, I worked as a ML engineer for a consultant in the Bay Area, and then before that, I was a high school teacher in Connecticut, so wearing the New Haven shirt, shout out to any Connecticut former or current residents. All right, so what's AutoML? I went straight to the source here, Wikipedia. Sorry, I'll read this to you and then I won't read again, but I think it's annoying when people talk over text, so I'll just read it. Automated machine learning is the process of automating the end-to-end process of applying machine learning. Wow, brilliant. In a typical machine learning application, practitioners must apply the appropriate data pre-processing, feature engineering, feature extraction, and feature selection methods. So this is not probably rocket science. AutoML stands for automated machine learning. It's taking machine learning and it's automating it. Like, no duh, not very complicated. But we're going to try to talk tonight about kind of the steps in the process. And so this concept of a data science pipeline or a data analytics pipeline or an AI pipeline, where you're doing things like pre-processing and feature engineering and model selection, these are indeed relevant things that I think are definitely not trivial. So hopefully we'll scratch that surface a little bit tonight. And I put this up here kind of to that point. It's a little bit complicated. What does AutoML actually mean? So to this point, is this AutoML? So for the code, who here would describe themselves as like a coder developer? Who writes code like at least once a week? Show of hands. Okay, so thank you. For people who don't, sorry, I don't know. Code has a reputation as being ugly to look at. I'm not sure if that's true or not. But for those who are unfamiliar with code or algorithms or math, basically what we see here is a for loop. And this for loop is describing gradient descent, which is an optimization method for fitting a linear regression model. Not really rocket science. The point I tried to make here is that, like, way back when, if you wanted to fit a model, you had to like write things out on paper and keep track of parameters and keep track of values, and that was complicated. Like, is this AutoML? I don't know. It's just using a computer to help you. I wouldn't probably classify it as AutoML, but computers are powerful tools that do automate things. So it's complicated. I'm not sure if this is AutoML. This I put down as the recent past. I would imagine for developers in the room, this looks a lot more familiar. So for those who aren't familiar, we can see the top line here. You know, we're writing Python code, we're importing Python libraries. So hopefully people are kind of familiar with this, but the concept of a library, you're taking awesome work that other people have done, and you're just taking that prepackaged code and applying it to solve your own problems. So in this case, we're importing a linear regression class that someone else has already taken the time to develop for us, and we're just implementing this fit method on it. Life is good, we can move on. We're doing ML in a much easier, more brief fashion. Again, I might say it's AutoML, I might not. I'd probably not call this AutoML. The present looks like this. Sorry, I said this wouldn't be a sales pitch, but these are screenshots from Dataiku. So what does a data science platform look like? If you squint, for people in the back, sorry, you probably can't see this. For people in the front, maybe you can, but basically we can see things on the left like what features are being chosen as inputs to the model, how they're being pre-processed with things like missing value imputation and feature rescaling. And then on the right, you can see all sorts of algorithms that a developer can just pick with the click of a button. So it used to be that you had to write code. Now the present is a developer just says, hey, I want to run a linear regression. I also want to run a random forest model. They don't have to write any code. They just click a button. And so that might be great. It might be terrible. I'm not sure what you think. We'll get around to that later. And this, I think, is the future that everyone's looking for. Ideally, we'll get to a world where we have data, we pass it into some AutoML solution, and then out comes a model that is hopefully good. And by the way, again, just to be clear on terms here, when we talk about models, we're talking about predictive models that are taking data as inputs and presumably either predicting a particular output class, whether it be a supervised or an unsupervised learning model. So how does AutoML work right now, and how should it work going forward? Again, I'm kind of echoing Wikipedia here, not very original, but I would say, again, AutoML takes a few different components. First of all, you need data prep. Second of all, you need feature generation. Then after you generate your features, and by the way, feature is just a fancy term for what? Column names, great, love it, column names. That was the best answer. Yeah, so when you have inputs to a model, those inputs are typically stored in columns. So features are fancy names for column names, but you have to generate those columns. Once you've generated all the columns, you have to select the columns that you want. You have to do feature selection. So we don't say columns from now on, we'll say features because it sounds cooler. And then after you've selected the features or the columns that you want to put into your model, you have to do model selection. So before I was talking about random forest algorithms or linear regression algorithms or deep learning neural net algorithms are very sexy. These are different classes of predictive models, different types of algorithmic methods. Which one do you want to use? That's what I'm referencing here by model selection. And then there's this mouthful, this concept of hyperparameter optimization, which if it looks intimidating and boring to you, you're out of luck because we're going to talk more about this tonight. If hyperparameter optimization sounds super cool, you can have some wine afterwards and talk to hopefully someone who comes in the door later and say, I know all about hyperparameter optimization, so I at least sound smart. So again, what the heck is, we understand the word optimization. Hyperparameters, can somebody else help me out? I'm feeling lazy. Can somebody define what hyperparameters are?
Model tuning parameters.
Model tuning parameters, great. I was going to say, it's okay if you don't want to. It's my job in theory to do this. But yeah, model tuning parameters. In general, when you choose an algorithm, algorithms have certain parameters or certain design choices that are made about the constructs of the algorithm, like what's the space that you're going to explore when you fit that algorithm, and choosing kind of those constructs, those limits on the algorithm. That's the concept of a hyperparameter, and so optimizing that, it's kind of choosing the appropriate space to explore when you optimize your model. So you're figuring out like the space that the model can work in, and then once you've defined the space or the playground, then you go ahead and you train the model, which is in that space, finding the best predictive model given your data. And so a simple example here, I'm sure many people in the room are somewhat familiar with neural networks and this concept of deep neural nets, and they have different layers where data kind of passes along to different layers. So a trivial but hard to optimize hyperparameter for neural nets would be the number of layers. Does it get passed to one layer, or to two, or to three, or to infinity? And right there you can kind of start to see why hyperparameter optimization is quite the challenge, because the choices are infinite. Right? There's no confined space. You could choose to make to test out 1 through infinity, or 1 through infinity minus 1 number of layers for your deep neural network. And that's a lot of different choices to try out. So what's the best one? What's the one that's going to give you the most performant model? That's really like the crux of the issue. And so that's why I want to talk a little bit more about hyperparameter optimization, because it's the nerdiest, it sounds the most impressive, and it's actually, I would argue, the most challenging, perhaps. You can disagree with me on that. So just to be clear what we're doing and kind of what the state of this looks like right now, I also want to say that AutoML, even though I work for a company that provides AutoML solutions and I'm somewhat familiar with the competition, I would say the world and the state of AutoML is not that awesome right now. So if you're looking to start a cool company or just be great, and you want to make awesome contributions to AutoML, I think there is room for improvement. So right now, things that happen with data preparation, right now AutoML will do things like the conversion of text. So if you pass in a column of text, algorithms can't understand text. So we have to do things like tokenize that text, convert it to something like a TF-IDF matrix. We can talk more about that later, but the point is you have to take inputs and convert them to numbers. That's something that you used to have to do by writing code. Now it's kind of trivial, just let an AutoML solution do it. Similarly, categorical variables, those are things that are not numeric. You have to convert them through something like one-hot encoding. It was always painful. It was always stupid. You're wasting your time because you knew you needed to do it. Now you can just have an AutoML tool kind of pre-canned do that for you. The more interesting things that AutoML solutions do not do, you see on the second line here. Shout out to my French company. You can see, like, do you decide to merge mademoiselle and madame in your data set? Like, are those semantically similar enough for your algorithm? Or like, no, those are very different things, and that meaning should be differentiated when training my model. That's the sort of stuff, as I put down here. Actually, I didn't write it there, but this concept of like semantic meaning, like what does it mean? Is that meaning important for your algorithm? Those are decisions that, at least at the moment, I would argue fortunately for us all, humans still need to think about. And if you are a data scientist, I would say this is something that if you're being paid a lot of money, hopefully you're justifying it by doing a good job of making judgment calls like this. Like, do these semantic details matter, and how do you process and prepare that data for your predictive algorithms? Feature generation. So this is really boring. Again, some solutions are slightly more sophisticated, but oftentimes when people talk about feature generation, they're just saying we took column A, we took column B, and then we multiplied them together to make column C, and we also put in column C in your model. Why did we do that? I don't know. Sometimes it turns out that multiplicatively combined features are more performant, but like it's not super rooted in literature. It's just like low-hanging fruit. It seems like it's easy to do. We can automate it, so we do it. If we have column A, we have column B, we might add in column A plus B. Again, I would call that fairly boring. And again, as I said here, you still need to do the hard stuff. Like, think about your business, think about the model, and then think about how I can combine these features, maybe with some additional outside data to construct a semantically rich feature. Feature selection here. This is actually, I would say, kind of good, maybe. There are some judgment calls to be made here, but things like removing redundant or highly correlated features, or low information features, or high cardinality features. So high cardinality features when you have a categorical variable with option like low, really, really low, really low, really, really, really low. These are all different categories. And if you have many of them, that's high cardinality. And when you convert high cardinality categorical variables to numeric, at the moment, they just do a crappy job when they're put into machine learning models. So typically we say, this has got like too many options, and we need to merge them or get rid of them or something. Again, that's something that AutoML solutions can handle quite nicely. Model selection. I would love to talk to people about this afterwards. My understanding is that even model selection, which seems to me like there's real potential there, no one's really put a lot of time and energy into this and really cracked the case. Dataiku, we try to think about this intelligently to some extent, though we could probably do more. Thinking about what's the input, what's the output, what are the features, and given what we know about past models, how can we choose and recommend a model to you that's likely to be performant given this setup. That's something that we could do, but there's not a ton that's gone on there yet. So another room for further improvement. And then hyperparameter optimization. So there's a few different ways to do this. First of all, you could search the hyperparameter space, I said here, exhaustively or intelligently. So this concept of exhaustively, we were talking about deep learning models, and they have 1 layer or 2 layers or 3 layers. So an exhaustive search, sometimes referred to as grid search hyperparameter optimization, because you're kind of searching every element through some grid of potential hyperparameters. Exhaustive search is just trying 1 layer, training a model, and seeing how a 1-layer model performs. Trying 2 layers, training a model, and seeing how a 2-layer model performs. Trying 3, and so on and so forth. So that's good, I guess, because it's rigorous, and you get to see how every potential hyperparameter performed. But that's bad because every time you try to pick a hyperparameter, optimize your function on your data, that's a costly process. Costly in terms of time, money, compute resources. It's not easy to do. So in general, you probably don't want to search your hyperparameter space exhaustively. You probably want to do it intelligently. What do I mean by intelligently? We'll talk about that in a minute. And I put down here neural architecture search because I'm very interested in it, but know very little about it. If you know about it, please teach me something about it later. But neural architecture search, as far as I can tell, kind of is the process to designing the entire architecture of deep learning models and then optimizing models for certain architectures. Okay, so like math calc 101 or something, how can we optimize an objective function? So an objective function is like you have some function, you want to find like the maximum or the minimum, the best or the worst values. Like what are some ways to optimize? I think we're running slightly short on time and there's a bunch more that I want to get through, so I'll give you some answers. First of all, you could find a closed form solution. Okay, this is getting quite mathy, probably slightly annoying, but this is maybe what you did in like algebra class in 8th grade or something, right? If you have some quadratic function equal to 0, you use the quadratic formula. That's a closed form solution that tells you the values that solve this equation. They're A and B. There you go. You've got the answer. It's nice and easy. Closed form solutions are not super popular in the machine learning world because they're really hard to do computationally. So we're kind of going to forget about closed form solutions. Also, there's this concept of gradient descent. If you don't know what gradient descent is, but you're interested, go Google it. It's cool. It's important, but we're not going to talk about that now. There's also a concept of modeling a surrogate model, which I want to talk about now because that seems a little bit weird, exciting. Maybe you've never heard of it before. So we're going to talk about this concept of modeling a surrogate. Hopefully when I'm done, you'll understand what I mean. And we're going to use Bayesian methods to do that. So again, if you don't know anything about Bayesian methods or Bayesian optimization, it's interesting, it's cool. You'll get some of that from me tonight, but not enough. So you can add this to your list of notes. Go Google, was it Thomas Bayes, and learn about him and the things he did and the stuff he had to say. I wrote some pseudocode here, but again, code kind of sucks, so let's skip that. Or actually, before I skip that, let's do one thing. I'm talking about this concept of objective functions, and again, I just want to reiterate that objective functions are expensive. So the objective function is once you have your algorithm and you have your data and you're trying to build a predictive model, you got to train that model. Given a fixed set of hyperparameters, you got to train the model. So this is the stuff when you read about Google taking like a week to train a model on TPUs, tensor processing units. Like obviously that's an exception to the rule, but still it takes a long time. It's not easy to do, to train a model and then evaluate that model on like some sort of held out data set. So it's not so easy just to say, let's try out every hyperparameter by training a model, by assessing the objective function. That's not trivial to do, so we want to do it as little as possible. So let's move on from this code and use pictures because they're more fun. So I said it was a teacher before in my past life. So if someone submitted this to me, I would say, this is crap. So what's crappy about this?
It's not very well labeled. Yeah, no X and Y.
Awesome, yeah, no labels, right? So I mean, like, how are you supposed to situate yourself as a viewer of this presentation if you don't have access labels? So let's get them there. What are they? And I would posit that the vertical axis labels are going to be kind of tricky. Maybe some really astute people in the crowd can figure out what should go on the vertical axes, but maybe I'll give you a hint. The horizontal axis, it's the same for both graphs. Any guess what the horizontal axis should be? Like, what are we talking about? What's on the horizontal axis? Good guess. No, not that. I shall tell you. It's the hyperparameter value. So we're talking about hyperparameter optimization. So it's the hyperparameter value. Sorry, maybe this is a little bit hard to read. The vertical axis on all the left-hand graphs is what I'll say, it's the objective function output, and the vertical axis label on the right-hand graph is this concept of what I'll refer to as expected improvement. And so you can see here, if you squint, again, sorry, colors are probably bad, but I think at least people in the front few rows can see. If you're in the back and you care, come up, because this is kind of cool. If you don't care, no offense. But the yellow line here, the yellow line, it says, is the noise-free objective. So what the hell's going on? The yellow line, it's the same for every graph because the noise-free objective function is the same. It's basically telling us if there were no noise, and we'll forget about that concept for now, and we evaluated the objective function with every hyperparameter, so all the hyperparameters from left to right, we would get this yellow line. So truly, like, what hyperparameter should we use to train our model? That's a hard question. Can anyone answer it off the bat? The answer is here in front of you, roughly. Close. Can you put a negative sign in front of that? Yeah, negative 0.5. Is there a laser pointer on this thing? Let's find out. No? Oh, yeah, there is. There it is. There it is. Okay, so in this case, if you choose a hyperparameter of negative 0.5 or roughly negative 0.5, in this case, it corresponds to the highest objective function output. Again, astute viewers would recognize that this should probably be like flip down. Usually you want to find minima and not maxima, but forget about it. In this case here, you could see a hyperparameter value of negative 0.5 corresponds to a high objective function output. So this is just saying when you have a hyperparameter value of negative 0.5 and you train that model, how performant is your algorithm that you have just learned or trained? This is saying for a hyperparameter value of negative 0.5, it's great. You did really, really well. If you pick other hyperparameter values like 2, and then you train your model, how predictive is your model? This is showing us, since it's really low, a hyperparameter value of 2 does a crappy job. So like 2 would be a bad hyperparameter value to choose. You could choose 2, you could train your model, and you could optimize the parameters in your model, but you could have chosen a crappy hyperparameter value. So you don't want to choose 2, and that's why this is so hard.
Is this any hyperparameter?
Yes, we're just talking like generic. So here you go. There's the yellow line. That's our noise-free objective function. And so I mentioned this term surrogate previously. The concept of a surrogate function is we pick some prior distribution. This is where Bayes is coming in. Some simple distribution, which is our guess as to what truly that noise-free objective function looks like. And so initially we make some ignorant choice. We just make this uniform guess. We say, we don't really know. It seems like maybe every hyperparameter is equally performant. That's indicated by this horizontal line. Whatever hyperparameter you choose, we guess going in that it's all the same. We're going to get the output on the objective function. It's going to be all the same. That's kind of our baseline starting point. And then we are going to refine that as time goes on. So, step 1, we set our prior distribution. It's the blue thing. So we just say, I think, hyperparameter doesn't matter. Whatever hyperparameter value I choose, the objective function is going to have the same output. So I'm choosing this blue line. Step 2, in this algorithm, we take samples and we evaluate the objective function. So we take samples, in this case, samples of our hyperparameter distribution. So the first sample we took is like -1 roughly. The second sample we took, it's a little over 1. So we take those samples of hyperparameters, we pick the hyperparameter -1, we train the model, we see how performant that model is. It looks like it was not that great. We take a hyperparameter of 1.1, we train the model. How good was the model that used a hyperparameter of 1.1? If you squint, you can see maybe it was slightly better than a hyperparameter of -1. So that's what we did to start. So now I'm just like glossing over a lot of stuff here. This is where, you'd say like ... math. But in general, what I'm doing here is I'm combining the acquisition function, which is just a fancy term to say, how do we search for our next point? Combining the prior distribution, which we kind of talked about previously, and the known points to determine what sample to try next. So this looks complicated, but I think we can actually figure it out here. So if you see, we chose a hyperparameter of -1, and we didn't do very well. We picked a hyperparameter of 1, and we did slightly better. So here in this case, we're saying, actually, the next time we try this, we should try a hyperparameter of 2. Why a hyperparameter of 2? Because we're kind of making this naive assumption that if we chose -1 and it was a little bad, and we chose 1, it was a little bit better, if you fit a line between these 2 points, it's like slowly sloping up. So our naive assumption right now is like, okay, it seems to us we have evidence that as the hyperparameter goes up, the model performance goes up. So in that case, why don't we just choose the highest hyperparameter available to us, in this case 2. So that's what we do. We evaluate the objective function at this new point and then update the prior distribution. So you can see here we thought that a hyperparameter of 2 would be good. And is a hyperparameter of 2 good? No, yeah, right. So it's down here, it's low. So our guess was wrong. So we made one more search of the objective function. In this case, we tried a hyperparameter. It didn't turn out that well. And so now we update this blue function. Now we say, okay, the blue function is clearly not a straight horizontal line. It seems like it's got kind of this curvy shape to it. And so now again, we kind of repeat the previous step and we say, well, there's this big area here between -1 and 1. We haven't searched there yet. In general, it seems like it's low, a little bit high, and then low. So our guess is like maybe actually the true function here is some sort of like inverted parabola. Maybe actually the best thing we should try is somewhere right around here. So you can see that here. So now we're saying, the expected improvement is maximized at like 0.4. So we should try 0.4. We tried 0.4 and was it that good? It was all right. The process continues. So we keep basically looking for the hyperparameter that's going to give us the greatest expected improvement, assessing that hyperparameter by doing a model train, seeing the performance on the held out validation set, and then repeating. So you can see here, basically over time, again, sorry this is quite small, but as the process continues, you can see what happens to the blue function. I will tell you. It gets close to the yellow function, which is the goal, right? We wanted to know what the yellow function was like, what the true hyperparameter space was like, but that would be really hard to do. So by only evaluating, 10 different model training sessions, we were able to quite well approximate the yellow true hyperparameter space. And so that's kind of a nice little hack that you get through Bayesian hyperparameter optimization. If you're still trying to piece this all together, I'll leave this up here. You can think about it while we have one question.
Yeah, I was just wondering if you could speak a little bit to what the blue shaded area represents in the graphs on the left.
Great question. Anybody have any guesses as to what the blue shaded area means?
The space that you expect the function to potentially be within.
Yeah. So confidence interval, space you expect the function to be within. So again, we're saying here, like between -1 and 1, we think maybe it could be good, but it's a big space that we haven't assessed yet. Ergo, this blue area is really hot. It's really large. We're not really sure if it's going to be good. Whereas, as we continue, you could see this blue area, suddenly it's getting really small because we've assessed many points and the uncertainty is going down. Sure, I'm happy to do questions, whatever.
No, this whole process your AutoML can do at the moment, or this is a manual process?
Yeah, so this is a process that I would say is well suited for AutoML, and Dataiku and other solutions provide this sort of hyperparameter optimization. Basically, you would say, I have this model, I have kind of a range of hyperparameters. So here you can see I have hyperparameters ranging from -1 to 2. So you kind of give it those constraints, and then in the background, these computations can run, and then we'll say, okay, we did all the work, and we found the best hyperparameter was -0.5. So this is something that's a real pain in the butt, really important. There's a lot of work going on, but it's well suited towards automation. So I would say this is something that you should demand of your AutoML solutions. Yeah?
So why is data drift not an intrinsic part of how AutoML works? Because as the underlying data changes, your model selection from top to bottom changes, right?
Good question. So typically if we think about and that's why I mentioned that we were going to ignore this concept of noise-free. But so here you can see the noise-free function is yellow, but the first time we assessed hyperparameter like 1.1, it didn't fall on the yellow. Like in general, the points we choose fall on the yellow. The reason they don't always fall on the yellow is because we're taking, typically when we do model training, some sort of held out randomly trained set, and then some sort of randomly held out test set. And so therefore, the randomization that we're using to train and to test our model performance can lead to this deviation. So you're talking about model data drift. I would say it's probably not, because you're typically doing like random subsets of your training data for a particular hyperparameter optimization. how I interpret data drift, it's not really an issue. But if you're talking about I and my organization am training this like customer loyalty model every day or week or quarter, I don't know how often you're doing it, but for those who are unaware, correct me if I'm wrong, but my understanding of what you're referring to as data drift is this concept that there's something in the universe that's changing. The customers that come to my organization are changing. The data is changing. The data is drifting. Therefore, the hyperparameter that was best suited yesterday or last week or last year, it's not the same anymore. So to solve that problem, I would just say you should have your models on a retraining schedule. Just do this process, but every so often to make sure that your data is fresh.
So because your competitors have flags for data drift now, and they flag it out. I work for a CPG firm, so for us, data keeps on changing.
Yep.
The way things are behaving. So I'm just curious to know whether you have that factored in your platform.
Yep. Yeah. So we do. We're aware of this, and now Dataiku does as well have some functionality to assess the fugacity score, which has to do with data drift, which I'd never heard of before, and I still can't give you a good lecture on what fugacity measures, something about the difference in distributions. But so we have addressed this concern. There's more that we could do, but we've done something. Yeah?
Is it only one hyper parameter, or can you have more than one?
You can have more than one.
Okay, so.
But it gets harder, right? So the more you have, like right now we're searching kind of a one-dimensional space, just this horizontal line. But now you can think about this in crazy multiple dimensions because we need to be thinking about this not just in 2D but in ND, and it's harder. But the math is the same, which is nice. All right, I have a couple more slides. We can do them. I'll finish. We can ask more questions or do whatever you want. So really quickly, when should you use AutoML? According to me, the authority on this subject, you should use it when. In all seriousness, I say this when I'm selling our AutoML solution. I'll say, hey, if you want to build quick prototypes, it's great. If you want to get baseline model performance, I think AutoML is a nice tool for that. So just like, how good could this predictive model be? For people here at BetaWorks, I would imagine that might be useful. I don't know exactly what everyone in the audience does, but particularly if you're a more nascent organization that's thinking about trying out new predictive models, and you're like, hey, how good could this actually be for our organization? Instead of hiring someone, paying them a lot of money to run a failed experiment for you that costs a lot of money, just use AutoML like fail fast. This is a good example of failing fast by getting a baseline and seeing like, okay, an AutoML solution already would be reasonably valuable to our organization. Therefore, let's implement the AutoML solution, or let's hire someone to refine it. But if AutoML really sucks, like you're starting with a bad baseline, that's going to be not good for you going forward, most likely. Ensembling. So ensembling is this concept of taking one predictive model, taking another predictive model, which is in theory, ideally, somewhat different, and kind of combining those two. So if this model says the answer is 10, this model says the answer is 20, then you combine them and you say, okay, maybe the answer is 15. Speeding up monotonous tasks, I referred to this earlier, like one-hot encoding of categorical variables. If you are a developer yourself or you manage teams that have people who are writing code to do this, I would argue that they should spend their code writing time on more valuable things. There's maybe a rebuttal to be made against me, but don't try to make it. And then lastly, provide advanced capabilities to users previously unequipped. That's just like kind statement for saying if you have someone who's never written Python code in their life, but they want to try to implement a random forest model, like they shouldn't feel as though that task is off limits to them by using AutoML. Now they can, so that's great. I think this is my last slide. When should you not use AutoML? I would argue 3 times. If you can't risk building something that you don't understand. So this concept of like black box, white box, explainability, machine learning, AI, and it's all kind of BS as far as I'm concerned, because some people say things are black box, but they are somehow interpretable. Some people say things are white box, but like you don't fully know everything that's going on. So don't buy into the hype, but nevertheless, if you really need to understand as much as possible about your predictive models, then you should probably have someone who's thoughtful, writing code that they can explain to you line by line when someone comes knocking. Or you could hire someone who understands the AutoML. That could work too. Causality and interpretability. I don't know why I put this one here, because to some extent I feel like models that are trained through AutoML technologies can help with interpretability. Causality is a whole other thing that machine learning doesn't do very well with, so just don't use ML or AutoML if you want to assess causality. Maybe, I don't know. And then lastly, if you're trying to advance the state of the art. So like Google's right around here somewhere, right? When Google's building new vision models, like they're not using AutoML, they're writing code. So that won't work. So here's some lovely screenshot of Dataiku. In all seriousness, if you have small teams of developers, you're struggling to build algorithms, maintain those algorithms, kind of collaborate in your data product building needs, Dataiku could be a cool solution for you. If you're just interested to see like what the heck are these, so this gentleman over here works at a large CPG organization, like, or maybe it's large, I don't know, but oftentimes, yeah, it's large. Typically, these sorts of solutions are being used by large firms, whereas smaller organizations are probably just using like Python and scikit-learn. If you want to see what's going on inside like a lot of the big banks in Manhattan, like they're using a lot of stuff like this to do their data development. So it could be a good learning opportunity for you. And I think that's all I got. Thank you for your time.
Awesome, thank you, Will. So if anyone's got questions, we'll run around the mic just to make sure everyone can hear the questions. So, all right, heading over there.
Yeah, hi. Thank you for your clear slides. I was wondering if you could compare different AutoML solutions that are out there. Like AWS itself has seems to have a lot of AutoML, H2O, and Dataiku as well.
And now we talk about bias in machine learning.
Yeah. What can I say that's accurate and useful and not biased? I don't know. I don't actually have a lot to add on this. Like, I'm not intimately familiar with all the different capabilities. I guess one thing I would say, which is hard, but working for an enterprise B2B software provider, like I'm sure you all know, like marketing is real and marketing speak is real. And marketing speak can be problematic when you're actually searching for technical solutions. So I'm not intimately familiar with the code base of even Dataiku and all of our competitors. I'm more familiar with our own code base. But people make big claims, and the problem is, like, how do you validate them? That's not a trivial thing to do, but I guess I would encourage you, which hopefully is obvious, like, don't believe everything vendors say.
I had the same question.
Okay.
And another thing, I guess, on that point, which is potentially appropriate for this audience, these tools can be really expensive. In fact, most, if not all of them, tend to be fairly expensive, but they have different pricing structure, like what you're paying for, how you're paying. So in addition to trying to do your homework to understand what the capabilities of a particular tool are, it's also, I think, useful to understand how much it's going to cost you, and like, if I do more of X, it costs me more, versus if I do more of Y, the cost is capped. I think those sorts of incentives are something that you should be aware of if you're buying solutions in this space.
I'm seeing the picture here. Is it really like drag and drop pipelining, putting everything together, or are you writing some code somewhere in what language, or is it Dataiku language or something like that?
Yeah, no, indeed, we have proprietary visual data transformations that you can use, or you can write SQL, Python, R, any sort of variant of Spark or Hive code. So kind of for coders and clickers, as we say.
So I would love to jump back to a slide you had at the beginning of the presentation when you were talking about what AutoML can do and what humans still need to do, like the Madame versus Mademoiselle.
Yeah.
I just wanted some clarity, especially for the last 3 points you had up there, about what the capabilities are right now with what AutoML can do and what is still needed, like what you still need humans for.
As they would say in France, bof, je sais pas. I would say the feature selection is good, right? So, yeah, all of these vendors that we're talking about / not talking about, like, I think most of them can do a good job of feature selection because it's pretty trivial. It's like, not only can you do these things that are listed here, but for dimensionality reduction techniques like principal component analysis is the big one that people often refer to. Like those are things that, again, are just easy to throw math at, and you get an output that you can then use and have some confidence that it's useful. I would say the model selection, not so good. And I would say hyperparameter optimization, okay, I don't know. I mean, like the method that we talked about today, to my limited understanding, is kind of still the gold standard for hyperparameter optimization, which is still maybe lacking in some, like it takes a long time to search through, as that question mentioned, a large hyperparameter space. So I think there at the moment you're just kind of in a tough spot if you're trying to like navigate a large hyperparameter space. Though another thing I guess I would mention is this is in theory what academia is for, and I think there are researchers who are doing work and are saying we have found that for this type of prediction problem, like you might want to use a max depth of tree that is roughly this large because it's worked well in the past. I don't think that was a great answer, but you'll have to live with it.
So I had a question. First of all, we are a coding shop. We are not dependent on AutoML. Secondly, how efficient can neural networks be in terms of small data sets? Because small data sets are a big challenge for a lot of industries, especially ours. We really need to work with smaller data sets, let's say just 150 instances, and we have to predict. But the features are very robust, 150 features as well. So it's a square matrix. So, and there are a lot of firms, a lot of small startups which promise very good results with deep learning on small data sets. Do you have any specific insights on that, and can the platform help us do that?
I would say no. I would say that is, as I understand it, an exciting area of research, like this idea of like one-shot learning or low-shot learning, to basically try to learn things without billions and billions of rows. But I'm not intimately familiar with that literature. I know it's just something people care about. The one thing I would say that I've done in the past with good success is transfer learning, so using a pre-trained model that may well have a really large and complex, in this case, deep learning architecture, and you say, like, let's take all of the weights and biases that Google has trained, and then let's just retrain the last 1, 2, or 3 layers and kind of use the higher order abstractions that Google's model is developing as like input features for our final prediction. So transfer learning would be my recommendation, but I don't know, read up more about one-shot learning, I guess.
Since this space is moving so rapidly, if you were to put on your vision hat, can you imagine in a few years from now where AutoML kind of takes off and really almost makes people unnecessary? Are we going to see kind of a singularity where the ML creates the ML and it just goes off the charts?
I would say yes and no. I think that, right, you've seen a trend towards going from, like, coding has gotten easier and easier and easier, right? You used to have to like compile your own code. Now writing Python is trivial, but oh wait, now I'm telling you maybe you don't have to write Python code anymore. So I do think that's a trend that's not slowing down, though I don't think actually getting in and being a coder is something that will die. And also to the question that was asked earlier, I still think for a long time, as far as I can tell, just being thoughtful about what you're inputting into your model and how you're actually hypothesizing, like, this variable might be correlated with that variable. That's a decision that, you know, you're making a very high level decision that you can then let an AutoML method assess for you. But that high level decision that, like, hey, I think these 3 variables could be good predictors for our organization, let's try them. Like, that's something that's still requires, as people always say, like domain knowledge, domain expertise, and also some understanding of statistics. I think that's going to be valuable for some time. I think I can shout your question out. If you just tell me, I can. Yeah, you.
It kind of relates to both of these guys. Like, do you have sampling strategies that work best with AutoML?
Do we have sampling strategies that work best with AutoML? Yeah, we can do things like rebalance imbalance classes, stuff like that, stratified sampling, stuff like that. So I don't know if that's sexy or not, but in general, it's useful.
But are you picking them? Like, do you recommend getting your service to pick it, or is this something that's like part of that human?
I think in Dataiku at the moment, if you want to do like class rebalancing, so you have a super imbalanced data set, right? So you have like lone defaults, and most people are not defaulting, and a very small percentage are. I think that we don't do class rebalance sampling by default, but you click a button to turn it on.
Okay, last question.
Yeah, hi. One two-part question. One is, could you repeat what you said about 1 and 2, where AutoML struggles in data prep and feature generation? What are the problems? And also, does it do well with like the pitfalls like overfitting, which are common to ML?
The overfitting question is a good one, and I should have a good answer for you, and I would say I probably don't, so I apologize. Maybe let me get back to you on that. And the first two, I think, just to reiterate, data prep, like you have to make a lot of judgment calls when you're preparing data. How you deal with missingness is something that is a real issue that, again, kind of the literature is looking into for you. There are some best practices with regards to that, but still, there is room for human judgment there, and so therefore I feel like relying on AutoML tools for data prep, you can use the data prep, once you made a decision, like merge these values, like you can do that computation quickly, easily, and in a code-free way, but someone still needs to be at the reins making those decisions. And feature generation, I think this is probably where AutoML does worst in terms of thinking intelligently and saying, okay, given all the input data and your business domain and potential extra data we could acquire, this would be a really good feature to use in this prediction problem if only we had it. That's something, to the previous question, that I think is still, at the moment, very human-centric. And I think lots of people make claims that they're doing great feature generation, but to my knowledge, no one's really like doing amazing work there, but I could be wrong, so let me know if I am.